Good evening, students. Welcome to another video. Vedantu Karnataka. This is Catherine, your physics master teacher. How are you all doing? Students, can you quickly let me know in the chat if I am visible and audible? Let me also just check. Mhm. Hello, Beast Boy. Hello, Rija, Sana, Harihar Kumar. Good evening, good evening. I think I am. Right. Students, can you quickly send this link to all your friends preparing for exam 3 and ask them to quickly come join? Tell them that we're going to discuss most important repeatedly asked 3-mark questions in this class. Okay? Yes. I will wait for one more minute and then we'll start. I'm good. How are you? Yes, Uday, I remember you. Hello, Sheikh. Hello, Nishant. How are you all doing? Are you all fine? Are you all doing well? Oh, sorry, the subject is not mentioned. Okay, I am physics teacher. Okay, so I will be doing physics today. Add physics also on the thumbnail. REO. Okay, shall we start? Hello, Uday Gowda. Okay, Nishant. Okay, shall we start? Yes, let's start. Send this link quickly to all your friends who are planning to write exam 3. Tell them to start preparations. It is not a lot of time. You know, it's on 10th, right? 9th or 10th. So send this to all your friends who are preparing for exam 3. Ask them to come join us on live. Sheikh is not fine because of exam 3. Why? You already had 2 exams. Enough of practice. Oh, REO, welcome to Vedantu Karnataka. All of you say hi to REO. He's a new subscriber. Chemistry classes are already happening. They're taken by Pramila ma'am and Ankita ma'am. Okay, I'm your physics teacher. Hi Sunita. Okay, let's start. We will discuss 3 markers, only 3 markers in today's class. Okay. First question. Mention 3 basic properties of electric charge. One question that all of you should be answering, and that's been repeated so many times. Not sure if it will come this time also because it has been repeated a lot of times. Yeah. What are the 3 basic properties of electric charge? The first one, charges are additive, charges are quantized, charges are conserved. Now, for 3 marks, you actually don't have to explain, you just have to write that much additive, quantized, and conserved. Okay? Yes. Next question. Mention any 3 properties of electrical field lines. What are the 3 properties? There are so many properties. I've put 5. You can write any 3. Okay? Electric field line starts from positive and end on negative. You've seen that. If you have a positive charge, field lines are always moving out of the positive. Now, if you have a negative charge, field lines are always moving in to the negative. So, field lines always start from the positive, they move into the negative. And you can see that No two field lines go like this, or like this, or like this. They're always by themselves. They never intersect. Now, electrical field lines do not form closed loop. See, if this is a positive charge, this field line is not going to form a loop. It's just going to form straight lines outwards. So they do not form closed loops. Next one, electrical field lines do not pass through conductors and they can pass through insulators. Any three you can write down. So if you have a conductor, electrical field lines do not pass through them. Okay? But if it's an insulator, electrical field lines can pass through them. Okay? Okay. Students, 5-mark questions. You will have a class tomorrow. Same time, we will discuss all important 5 markers. Today, we are discussing all important 3 markers. And notes will be given after the class. Okay? So, after the class, if you go to the description of the video, there will be link to notes. Okay? Anything else? I think I've addressed all the doubts. Yeah. Okay. Next question. Malu VR, did you understand where the notes are sent? Yeah. Next question. Hi Preetu. What is an electrical dipole? Define electrical dipole moment, give its direction. See, all this in detail I've done videos. You can just check my previous lecture, which was dipole moment. Okay, the lecture I did before Gauss law. That is on the first chapter. There I have explained dipoles in detail. So now here it's just for 3 marks, so we look at only the points. So first one, what is an electric dipole? So if you have two charges, okay, if you have a plus charge and a minus charge, and you keep them at some separation, some distance, usually the distance is 2a, okay, then you call it an electrical dipole. So how does it work? So imagine you have a plus charge and a minus charge and you keep it at a distance of 2a, okay, then that is called electrical dipole. Now, what is electrical dipole moment? Electrical dipole moment is the magnitude of the charge. So, if these charges are q, what is the magnitude of the charge? It's q. And what is the distance between the charges? It's 2a. So, q into 2a is p, which is the electric dipole moment. Okay? And dipole always moves from negative to positive. Yes. Okay? Yes. So that is also a property of dipole. It always moves from negative to positive. Afira. See, what I've taken is I've taken previously asked, repeated 3-mark questions. Okay? So definitely you will get some questions from this, hopefully, because exam 3 is going to be different compared to exam 1 and exam 2. So let's just hope for the best. So these are all 3 markers that are usually asked. Okay? But as I said, it all depends on the examiner. So if one fine examiner feels like she or he has to give new set of questions, then we'll never know. But let's do our part. We'll practice whatever is available. Okay? Yeah. So yeah, these are 3 things about dipoles. That they always move from negative to positive. The dipole moment is Q2A, and the electrical dipole, what is an electrical dipole? Okay, next question. Derive the expression for the torque on an electrical dipole placed in a uniform electric field. Okay, so we have to find out I'm not very sure, Zara. I have to find out. Okay, I don't want to give you false information. I'm not very sure about that. Shake. Even if you start now, you'll definitely pass. You have like 9 or 10 days more, but you should start now. Okay? You shouldn't waste any more time. Start now. So, today, after this class, sit and make sure you are thorough with all the 3 markers. Okay? Tomorrow, you learn all the 5 markers. Maybe you'll need one more day to practice those. Okay? Thoroughly learn all the concepts, all the portions. You have enough time. Even if you start today, you will pass. Okay? But start today. Okay? Yes. Okay, now after some time, let's continue. Let's not waste a lot of time. So derive the expression for torque on an electrical dipole. So what, as I already said, what is a dipole? You have a plus charge and a minus charge that is separated by a distance 2a. That is a dipole. Okay. Now these two are charges, so they will have forces acting on them. So the force on the charge plus q will be QE, and force on minus q will also be QE, but the directions will be different because one is a positive charge, the other is a negative charge. But they will both have force Q into E. Okay. Now, what is a torque? So if you have to just keep my phone here, yeah. So what is a torque? Imagine you have an electric field. Okay. You have an electric field. This keeps happening to me in my class. I'm sorry. This goes. This comes. Okay. Yeah. So you have your dipole like this. Okay. I use milk. You have your dipole like this. Say there's a force in 2 different directions. So if this is your dipole, there is a force that's going to act on it until this dipole becomes horizontal. Okay. So if there's a dipole like this, there's an electric field, it has to become horizontal. It has to become parallel to the electric field. Till then there will be a force. And that force is what you have to find out. So how will you find out that force? It is nothing else but magnitude into perpendicular distance, which is QE times, if this is A, this is B. Okay. And let's say this is sine theta. That is theta. So this line will be AB sine theta. So QE into AB sine theta. What is AB? The length of the dipole. As I said, a dipole is 2 charges placed at a distance of 2a. So AB should obviously be 2a sine theta. So this becomes 2a QE sine theta. And in the previous question, we already saw what is 2 into a into q. It is P. So this becomes PE sine theta. Okay. Now to derive for the question, if it's, you might be, I'm wondering, ma'am, for 3 marks, should we do this much? The question is to derive the expression for torque on an electrical dipole. For that, you only have to do this much. That's all. You just have to do torque is equal to QE into AB sine theta, which is QE into 2A sine theta, which is PE sine theta. Okay. Yeah, there's a figure here as well in case you want to refer. So this is the dipole. See, one charge, second charge, this is angle theta, and then this is the, okay, in this case, this is the electrical field. Okay, so diagram is also usually important. It's good if you can draw the diagram as well. But for those of you who find it difficult to draw the diagram, please make sure you learn at least this part. Okay, this part is very important. Okay, next question. Mention 3 properties of equipotential surface. So first thing you need to know, what is an equipotential surface? Okay. An equipotential surface is when the work done in moving a test charge from one point to another is zero. Okay. So let's say you have one charge here. You bring another charge. Okay. So you bring another charge to this charge, and the work you do to do that, the work that has to be done to bring the charge is called, is always zero in an equipotential surface. Why? Because the potential is the same everywhere. An electric field line is always perpendicular to equipotential surface. No two equipotential surface intersect each other. Unstable, Zara has asked me what is meant by okay, yeah, sorry. Okay, Zara has asked me what is meant by unstable equilibrium for a, which one? This one are you talking about? What is meant by unstable equilibrium for torque on an electric dipole? See, one thing that you need to know here is, see, whenever there is a dipole in an electric field, until the dipole is parallel to the electric field, it will always have some force acting on it. Okay? And we know that torque is PE sine theta. So when it's in equilibrium, sine theta should be 0, which means it can be 0 or 180. Both are fine. So the dipole will be aligned with the field. So the dipole has no, nothing to interact or anything like that. The dipole is aligned with the field. That if it's not aligned with the field, then it is unstable. Okay? Then it's not an equilibrium, it's just unstable. See, this figure that I've drawn, this is unstable because now this black line has to rotate and align with the pink line. Only then it becomes stable. Okay, let's move on. What is a capacitor? Mention any two factors on which the capacitance of a parallel plate capacitor depends. Okay. A capacitor is what? A capacitor is a device that is used to store electric charge. Now, the capacitance of a parallel plate capacitor depends on three things: the dielectric, the area, the distance. So you might have already learned this. You should know this by now. The capacitance is equal to A into, what is the formula for capacitance? Relationship that you will, I think I put that question here. Okay, so we'll do that when we do that. Okay, anyways. It depends on A, epsilon naught, and D. Now, if there is a dielectric, you will have a factor K also coming into picture. So that is why it depends on dielectric constant. So you can see that the formula for capacitance, which is C is equal to A epsilon naught by D, changes when it is placed in a dielectric. What is a dielectric? So imagine I have a capacitor. I have placed the capacitor in air. Okay. And then I place the capacitor in liquid. Liquid is a dielectric. Let's say I put it in water. Water is my dielectric. So my formula C is equal to epsilon naught A by D is in, without any medium. Now, if I place this in a medium, there will be a K term to it. So these are the three things that a capacitor depends on. It depends on K. What is K? K is the dielectric constant. It depends on A, which is the area. It depends on D, which is the distance between the plates. 1, 2, 3. Very easy. You don't have to, remember each of these points. If you can remember the formula, you'll easily remember that. Okay? Yes? No? Are you all with me? Can you put some fire in the chat if you're all with me? Okay. Next question. Deduce the relation E is equal to minus dV by dx where the terms have their usual meaning. So we have to find out the relationship EV is equal to minus dV by dx. So here also, first thing, you have two surfaces. You see, this is the first surface, and then this surface below that is the second surface. I don't know if I can color that. Yeah, you can see two surfaces, one above the other. There are two surfaces here. So there are two surfaces, A and B. These A and B, both these surfaces are spaced. They're close enough. Okay. So the surface A has a potential of VA. The surface B has a potential of VB. Okay. Now, if the potential of surface A is V, okay, if the potential VA, let's say it is V, okay, then B will be V minus dV. What is dV? dV is the decrease in potential. So some of it is lost there. Okay, so if the first surface has a potential of V, the second surface will have a potential of V minus dV. Now, when a unit positive charge is moved from the top surface to the bottom surface. So, I should keep something here to explain all this to you. So, let's say this is the bottom, this is the top. Electric field is in this direction. Okay? Electric field is in the upward direction. Now, I am bringing a charge from the top surface to the bottom, which is against the electric field. I am moving a charge downwards. So, the work done is basically minus EdR. Now, what is dr? Dr is the distance between the two surfaces. The distance between A and B is dr. E is the electric field, but it is in the opposite direction. So I am bringing my test charge in the opposite direction to the electric field. If electric field is pointing up, I am moving my charge down. Okay. Now, we all know work done is by definition VA minus VB. Right. The potential of surface A minus potential of surface B. What is the potential of surface A? It is V minus the potential of surface B is V minus dV. Now, when you open the brackets, V and V cancels, you will get dV. Now, we also know that work done is minus EdR, and then you equate the two. Minus EdR is equal to dV. E is minus dV by dr. Very easy, right? Yeah, all of these are just, simple questions. The negative sign indicates that the electric field is in the direction of decreasing potential. What does that mean? I have two surfaces, A and B. A has a higher potential, B has a lower potential. Electric field is in this direction. So it's in the direction in which the potential is decreasing. Okay? Yes. Okay, so for 3 marks, what all steps do you write? You just have to write what is VA, what is VB, what is work done, two formulas, equate them, find out E. More than enough. Okay? Yes. Okay. Give 3 results of electrostatics of conductors. Okay, this also I have taught you in my last video. So in electrostatics, you have to tell me 3 things that you see in a conductor. First thing, the electric field inside a conductor is 0. Any excess charge on the surface of the conductor, any excess charge on a conductor resides on its surface. So if you have a conductor, all the charges will lie on the surface. Inside, the charges will be 0. 0 charges. And the electric field outside is perpendicular to the surface. So this is the direction of electric field. It is going to be perpendicular to the surface. Whatever point you take, it will always be perpendicular to the surface. And it's given by E is equal to sigma by epsilon naught. Okay. So, yeah. Okay. Next question. How long this video will be, I'm actually not very sure. 1.5 hours maybe. Derive the expression of the capacitance of a parallel plate capacitor. Okay. Now we will find out the value expression for capacitance. So, okay. Yeah. So a parallel plate capacitor, what is a parallel plate capacitor? It has two parallel plates. These two plates are conducting plates. Okay. And these plates are separated by D. Now let A be the area on each plate. Okay, let the area on each plate be A. Both these plates have area A. And the charges could be plus Q and minus Q. Okay, so you have two capacitors, two plates. They are at a distance of D, area A. They have charges plus Q and minus Q. First question, we will find out the electric field due to each plate. This could be one question. Find out the electric field due to each plate on a parallel plate capacitor. So we've already seen that the electric field is E is equal to sigma by 2 epsilon naught. So for the first plate and the second plate, it will be E is equal to sigma by 2 epsilon naught. So the total electric field is, you just add them, you get sigma by epsilon naught. So that is how you get sigma by epsilon naught. Okay. So sigma by epsilon naught is the total electric field. E is equal to sigma by epsilon. Now let's say what is E? We already know this is a formula from again first chapter. This also I've taught you in the previous video. So sigma is equal to Q by A. Okay, this has a derivation. So those of you who don't want to look into that much, you can just learn it as sigma is equal to Q by A. And then you substitute. So E is equal to sigma by epsilon. So this becomes E is equal to Q by A epsilon naught. This is the formula for electric field on a parallel plate capacitor. Next is the formula for potential difference between the plates. So first formula is potential difference is electric field times distance. Okay. Now what is electric field? In the last, we already derived it. What is it? QA by epsilon naught. So this is Q by A epsilon naught into D. Yes. Capacitance. C is defined as Q by V. Okay. So we have V now. So we have C is equal to Q by, what is V? QD by A epsilon naught. So Q and Q will cancel. So C will be A epsilon naught will go to the denominator divided by D. So this is how you get the expression for capacitance. This expression I already discussed earlier in this video itself, where you had to, the question was, give three things that capacitance depend on. Okay. So the expression is C is equal to epsilon naught A by D. So you can see clearly from this that capacitance is directly proportional to area. C is directly proportional to area. C is inversely proportional to the distance between the plates. Okay? Yes. Yeah. Okay, so that is the expression to derive capacitance. Now, if you were asked to derive potential difference or electric field, there could be three questions from this, three possible questions from this one derivation. Okay? Just this part. Yeah. Okay. Let's move on to the next question. Obtain the expression for potential energy of two charges in the absence of an electric field. Okay. Obtain the expression for the potential energy of two charges in the absence of an electric field. So what happens? Let the potential energy of a system of two charges, okay? It is the work done in bringing the charges from infinity to a distance r apart. So there are two charges here, okay? Now the work done to bring Q1 from infinity, from somewhere here to point A, okay? So if this is point A, the work done to bring the charge from some point to A. Since there is no electric field present, the work done would be zero. Here, there is no electric field. So, it's very easy to bring the charge from infinity to A. That is why work done is zero. First thing. Then, now you will bring Q2. See, I don't know if you're understanding this. Ma'am, I should study question wise per unit or study complete chapter. It will depend on how much marks you want. Okay? So, if you are planning to start studying from today and if you're planning to study only physics till 10, you have enough time. You can study chapters fully, you can study the questions also. But if you have no time, you study all the subjects, then start with questions. Okay? Start studying questions and then move on to concepts. But if you want to score very well, if you want to score very good marks, you have to study chapters. If you want to pass and score just what is required, then questions would be enough. Okay, so this one I will explain it properly. So initially, from infinity, I am bringing a charge to a point A. Okay, you don't have to study all chapters. You can check on weightage. You have a blueprint, right? On which chapters have how many marks. So first study all the high weightage chapters. Okay, yeah. So what was, yeah, charge. So plus Q is from infinity. It comes to point A. Okay. Now I have Q1 here. Let's not put plus Q. I will just put Q1. Okay. So work done for this is 0 from infinity to bring it till A. Okay. Now what I will do, but then here why there is no need of, there's no work done because there are no other charges. There's nothing for it to, there's no force to act on it. Now, second thing what I'm going to do, I will bring a charge Q2 from infinity to another point B. From infinity, I'll bring it to B, which is at a distance R from Q. So this distance is R. Okay? So work is done against the electric field produced by Q1. Okay? So if the electric field is in this direction, I am bringing my charge in the opposite direction. So work is done against the electric field. Now potential due to point B. Potential here will be what? What is the formula for potential? Okay. You might not see this part, no? Now can you see? Yeah. So potential V is equal to 1 by 4 pi epsilon naught Q1 by R. This is the potential due to V. Now, to bring Q2, the work done is the potential into Q2. So you can see that here. Q2 is equal to the work done in bringing Q2 is equal to V into Q2. What is V? 1 by 4 pi epsilon naught Q by R, Q1 by R into Q2. 1 by 4 pi epsilon naught Q1, Q2 by R. Okay. So what is the total work done? W1 was what? 0. W2 is 1 by 4 pi epsilon naught Q1 by Q2 R. So this is the total work done, and total work done and potential energy is the same. So the answer is the same. 1 by 4 pi epsilon naught Q1 Q2 by R. And the SI unit is Joule. So you might be wondering, ma'am, such a big question for 3 marks. It's not a big question. I just took some time to explain. The only thing that you have to do is, there is nothing initially. From infinity, you bring a charge Q1. There is no work done on it because it's just coming to a plain surface. Nothing is there. And then you bring another charge Q2. So this Q2 experiences a force because of Q1. And the force is, the potential is 1 by 4 pi epsilon 0 Q1 by R. Work done is 1 by 4 pi epsilon 0 Q1 by R into Q2. That's all. Okay. Okay. Next question. Derive an expression for the equivalent capacitance of capacitors connected in series. So let's say I have 3 capacitors and they're connected in series. Okay. So if they're all connected in series, I have to find out the equivalent capacitance, which is the total capacitance of C1, C2, C3, C4, F5, C5, how many ever are there. If they're all connected in series, I have to find out my equivalent capacitance. Okay. Now, on all the capacitors, what is same? There, the charge is going to be the same. Q, 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 Q. Okay? All the capacitors will have the same charge, but potential will be distributed. So you might have learned this in a series circuit. If my battery has 9 volts, and if I have 5 components, so this 9 volts is going to be shared between all of these components, right? So that is how it is going to be. So the charge, if charge is going to be Q everywhere, then which one should I put? Potential should be T. Potential would be V1, V2, V3, and V4. It's not going to be the same. And total potential V will be V1 plus, V2 plus, V3 plus, V4. It just goes on like this. We also have learned a relationship between potential, capacitance, and charge. What was it? C is equal to, we learned that here. This one. C is equal to Q by V. Yeah. Whatever you learned in a question, you're not supposed to forget it. C is equal to Q by V. Now from this, what is V? V is equal to Q by C. So V1 will be Q by C1. V2 will be Q by C2. And then it will just go on like that. So I get these equations V1, V2, V3. Okay. Now, if I substitute these equations in my main formula where V is equal to V1 plus V2 plus V3, what will I get? Instead of V1, I write Q by C1. Instead of V2, I write Q by C2. Instead of V3, I write Q by C3. And then I take Q outside. So what remains? 1 by C1 plus 1 by C2 plus 1 by C3. Okay. Now all of this I can take it as CS. So V will be Q by CS. Now what is CS? 1 by C1 plus 1 by C2 plus 1 by C3. Okay? Or what I can do is, see, this I can write it as, we know that V is Q by C. Okay? So instead of V, I'll write Q by CS is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. Q and Q will cancel, and that's how you get this equation. 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay? Yes. This is the total capacitance for a equivalent circuit with capacitors connected in series. Now the same thing can be asked for capacitors connected in parallel. So again, the only things that change here is in series, Q was constant, but here Q becomes Q1, Q2, Q3, but V is the same everywhere. Okay, so your formula Q is equal to CV. Formula becomes Q is equal to CV, and Q1 will be C1 into V. Okay, I want you to compare and learn the two. In series, what happens? In series, voltage will vary. Charge is going to be the same. That's because current is going to be the same. In parallel, voltage is the same. Current is going to vary. That is why Q1, Q changes to Q1, Q2, Q3. Voltage is always V. Okay? Yeah. So same thing. You have these formulas and then I'll substitute it in this. So what will it become? Q is equal to C1V plus C2V plus C3V. Now what is Q? I will just write it as CS into V. Okay, since it's parallel, I can write Q is CPV. So CPV is equal to C1V plus C2V plus C3V. So CP is equal to C1 plus C2 plus C3. These three steps are more than enough. I mean, this step as well and this. That's all that you need to write. So you will get CP is equal to C1 plus C2 plus C3. Okay. Give any three limitations of Ohm's law. What is Ohm's law? What does Ohm's law state? The very famous law that states V is equal to IR. That is, the voltage is always proportional to current if it's for a fixed resistance at an absolute constant temperature. Okay? So, Ohm's law is not valid at very low or very high temperatures, is the first limitation. It is only applicable to non-ohmic devices. It is invalid if current I has more than one value. In some materials, depends on the sign law. Yes, these are all direct questions. Mention any three factors on which resistance of a conductor depends. So what is the formula? Resistance is equal to rho L by A. So what are the factors that resistance depend on? Length of the conductor, area of cross section, and then nature of the material and temperature of the material. Okay? It depends on the temperature and the nature also. What is nature of the material? Resistivity. Other than these three terms, it depends on temperature also. You can just remember it like that. Okay. Next is to state and explain Kirchhoff's laws. So the question could be to explain Kirchhoff's junction rule or Kirchhoff's second law or the loop rule. So what is the junction rule? You have a junction. Okay, let's say you have a junction. Current goes in, goes out. Let's say it goes in, it goes out. Okay. So if this is I1, I2, I3, and I4. I3. So you have to decide on a sign convention. So let's look at according to this figure so you don't get confused. So here I1 is going in, it's taken as positive. So what all are the currents that are going in? I3 and I4. So I3 plus I4 will be equal to the currents going out, which is I1 plus I2. Simple. All the currents at the junction, the total sum of currents at the junction will be 0. So all the currents coming in will be equal to the currents going out. That's all. Now Kirchhoff's loop rule, it just says that if you take a loop, like this one loop, okay, sum of all EMFs and potential drops, everything together will be 0. So let's see, let's prove it. So first thing you should decide on a direction. So here the arrow is already here. So I'm going to take the same direction. So this is the direction. Now what I'll do is I'll start from here. Minus IR1. This is the first one. Minus IR1 because it is in the direction opposite to which I am moving. So I am starting from here. Okay, and I am going this way, but current is going this way, so I put it as negative. It's not in a way I like. So it's going in the opposite direction to which I am going. Next, I go, and then I reach here. So this is what? This is I2, but it's again in the opposite direction. So this becomes minus I2 R2 coming, and then battery is positive to negative. So this becomes plus E1. This is 0. That is for the first loop. Okay. Now for the second loop, what happens? Second loop. Can you see the second loop? Yeah. Second loop, what happens? Let's start from E2. Okay. Since the arrow, we're going this way. Okay. So we're going from positive, we're starting from the negative. It's along the direction of I3, R3. So I3, R3. And then I come. So this has to be if I'm starting from here, I3 is this way and I am moving this way. So minus I3 R3 plus I2 R2 so this arrow is wrong then, okay? So according to their figure, what they've taken is they've taken it like this. Okay? So plus I2 R2 minus I3 R3 and this will be minus E. Why? Because the measurement is in this direction. Okay? So I'll tell you in very easy steps. If the direction of current is in the direction in which you are moving, then you take it as positive. Otherwise, you take it as negative. Now, if the direction of the battery, the direction in which you are moving, on the way there is a battery. And when you enter the battery, if you're entering from the negative to the positive, you put it as negative. So imagine this is a battery. Okay. And you are coming, current, there's I1 here, okay, in this direction. And you are coming like this. So I1 is along your path, so you take it as positive. But when you reach the battery, you're going from the negative terminal to the positive terminal. So it becomes minus. Now, if the battery was ulta, okay, if the battery was like this, then it would have been positive because you are moving from the positive terminal of the battery to the negative. Okay? Alright? So that's all. That's Kirchhoff's laws. Whenever you go in the direction of the current and resistor, you take it as positive, otherwise, you take it as negative. If you're going in the direction of the battery where you're moving from the positive terminal to the negative, you take it as positive, otherwise, you take it as negative. You can actually write that. Now, if you're going like this, plus. Okay. Next question. Derive an expression for angular frequency of revolution for a charged particle moving perpendicular to a uniform magnetic field. Okay. So you have a charged particle and it's moving perpendicular to a uniform magnetic field. So obviously it will experience a force because it's a particle in a magnetic field. It will definitely experience a force and the force is given by F is equal to QVD. Okay. Now it says that it moves in a circular path. When something moves in a circular path, it always moves by centripetal force, which is mv square by r. So this mv square by r will be equal to F, which is going to be equal to BQV. Okay? Yeah, BQV. Now, V and V will cancel. MV by R is BQ. R is going to be MV by BQ. So from this again, when you rearrange, you will get V is what? QBRM. Simple mathematical substitution. Now imagine the question is for you to find time period. What will you do? Time is distance by speed. All of us know that. Now what is the distance? This is a circle. So the distance will be the circumference of the circle, which is 2 pi r divided by the speed v, which is 2 pi m by qb. This v you substitute from here. Okay? Some of you are wondering what is happening. So 2 pi r by v, which is 2 pi r divided by QBR by M. Yeah, R and R will cancel. 2 pi M by QB. Okay. And then frequency is 1 by time period. So it becomes the reciprocal. QB by 2 pi M. So this is angular frequency. Angular frequency is what? 2 pi into F. So you multiply 2 pi and then they cancel. So it becomes QB by M. Okay, next question. State and explain Biot-Savart's law with a suitable diagram. So the diagram for Biot-Savart's law is just this, a straight wire. It's a straight wire with current IDL and then this is okay. Let's say you have a current carrying wire and you take a point P at a distance R from the wire, okay? And there is a magnetic field dB, okay? There is current passing through the wire. The current I passes through the wire. I take a small piece of the wire, a small element dl on the wire, okay? And then Biot-Savart's law, that's all, that's the diagram. So Biot-Savart's law gives you the magnetic field produced at a point due to a small current carrying conductor. So as I said, you get the magnetic field at point P due to the small element dl. Okay. So L is the total current carrying conductor, but you will get the magnetic field due to a point P at a distance r because of a small element dl. Okay. Yeah. So what is the loss? I mean, mathematically the law is mu 0 by 4 pi I dl cross r cap by r square. What is dl cross r cap by r square? It is sine theta. So the formula is mu 0 by 4 pi I dl sine theta by r square. Now what is mu 0? 4 pi into 10 raised to minus 7. Next question. Students, question numbers are not correct. Okay. Yeah. Write a circuit diagram explaining the conversion of a galvanometer to a voltmeter. So to convert a galvanometer into a voltmeter, a high resistance R is connected in series with the galvanometer coil. So how do you convert it? V would be Ig into R plus G. Now what is R going to be equal to? V by Ig minus G. So what you're doing, you are connecting a high resistance in series. So if this is your galvanometer, you just connect a high resistance to it. That's all. Okay. Now to convert a galvanometer into an ammeter, what do you do? To convert, you take a low resistance, you connect it in parallel with the galvanometer. Okay. And then this becomes a ammeter. So I minus IGS is equal to IGG. So why all this? There are actually reasons behind this, but I'll be explaining them when I do the theory behind all this. So in simple terms, I can tell you this. An ammeter is a device that measures current. And current is always same in a series circuit. That's why ammeters are always placed in series circuit. So you have to do the opposite. So to convert a galvanometer to ammeter, you connect a resistor in parallel. Okay. Ammeters are always in series, but to convert galvanometer to ammeter, you connect a resistor in parallel. You can remember it that way. Next question. Mention any three properties of magnetic field lines. Yeah. What are magnetic field lines? If you have a magnet, North Pole, South Pole, magnetic field lines always start from North Pole and they go into the South Pole, which means they form closed loops. No intersections, one loop does not intersect with the other. And to near the magnet, the field lines are closer. As you move away from the magnet, the field lines become further away. That's because the magnet becomes less strong. So if I have a magnet and I try to stick something to it, the closer it is to the magnet, the more magnetic field strength it will have. That is because the magnetic field lines are closer near the magnet. As you move away, the strength of the magnetic field lines reduce. And they're all uniformly spaced. Okay? They're all parallel, uniformly spaced. Okay, next is they can ask you the difference between dia, para, and ferro. They wouldn't ask you everything. They might ask you how is relative permeability varied between dia, para, and ferro? Or how is magnetic susceptibility in dia, para, and ferro? 3 marks, 1 mark for each. Or they can ask you give 3 differences in para, give 3 differences in dia, give 3 differences in ferro. See, you can have so many questions from this one table. So this table is very straightforward, very easy. Okay. Next question. Properties of paramagnetic materials. So paramagnetic substances are weakly magnetized in the direction of the applied magnetic field. These substances move from weak to strong magnetic field regions, weakly attracted by magnets, susceptibility is small and positive, relative permeability is slightly greater than 1, magnetic susceptibility depends on temperature. Okay, these are all, common properties of paramagnetic materials. Same thing that we've discussed here as well. I mean, we've not discussed, I've put it in straightforward points. You can just write it down. Okay? Describe the coil and magnetic experiment of electromagnetic induction. Hi, Sana. Do you all know each other in the chat? Do you know each other earlier, or you get become friends after coming to the chat? Physics class buddies. Okay. Yeah. Magnet and coil experiment of electromagnetic induction. So that's very easy. You have a coil, you have a magnet. You keep moving the magnet in and out of the coil. So when you keep moving it, the galvanometer will deflect. You can see this coil. There's a coil which is attached to a galvanometer. Okay. And then you take a magnet, you move it of the in and out of the just a second. Coil. Yeah. So the galvanometer deflects only while the magnet is in motion. So when the magnet moves in and out, that's when the this thing moves. The galvanometer deflects. When the magnet is stationary, okay, so this is a coil and the magnet is stationary, then there is no deflection. The magnet galvanometer does not deflect. Why a galvanometer deflects? So, yeah, some of you might not know that point. See, galvanometer is a device that detects currents, very small currents, not like an ammeter, but it can detect very small change in current. That is why it deflects. So whenever the magnet moves in and out, there is a variation in current. That's why it deflects. So faster the motion of the magnet, higher the deflection. Same effect occurs if the coil is moved and the magnet is stationary. Anyhow, there just has to be movement. Initially, coil is there, magnet is moved. Otherwise, magnet is there, coil is moved. Any one is fine. Okay? So, what is the conclusion? The relative motion between the magnet and the coil that induces current demonstrating electromagnetic induction is what is done in the experiment. Okay, next question. Lenz's law as a consequence of law of conservation of energy. What is Lenz's law? Lenz's law states that the direction of the induced current is such that it opposes the change in magnetic flux that causes it. So, let's say the direction of the induced current is opposing the change in magnetic flux that it produces. I have put a simple explanation also here. So when a north pole approaches a coil, let's say this is a coil, this is a magnet, this is the north pole. So the north pole is approaching the coil. Okay? Magnetic flux through the coil increases, current is induced in the coil, and there is a magnetic field. Okay? The face of the coil becomes north pole. Here it becomes north. So what happens? North and north repels. So north is going in, but suddenly the coil repels it. Okay? Now what happens? Okay, this is the first thing that happens. Now, so because it repels, what happens? I move the magnet back. Now what happens? This suddenly becomes south. It tries to attract. It does not allow you to go. See, it's like what do I say? The coil is like a very mean person. When the magnet tries to come in, it does not allow. When the magnet tries to go out, that also it does not allow. Okay, so if the magnet tries to come in, then it becomes the north and it tries to oppose the motion. So the magnet says, okay, fine, I'll leave. So when the magnet tries to leave, then the coil becomes south and say, please don't leave, let's attract. Okay, so that is what it means by direction of induced current is such that it opposes the change in magnetic field. This explanation is given here very clearly. Okay. Okay, next question. Derive the expression for motional EMF induced in a straight conductor moving perpendicular to a uniform magnetic field. This is again very easy. So, motional. Okay. So, let's say you have a conductor. The conductor is moving in a magnetic field. There is a potential difference. The potential difference across a moving conductor is called motional EMF. Okay. What is motional EMF? It is the potential difference across a moving conductor. Okay. Yeah. Now, if you consider a rectangle, if you consider this rectangle, P, Q, R, S. Okay. With a conductor PQ. This is a rectangle. And this pink color PQ is a conducting rod. Okay. L is the length of PQ. L is the length of PQ. X is by how much PQ moves. So PQ can move this much. This is X. Now magnetic flux is how many magnetic field lines are there. So B into area. So magnetic flux is BA. What is the area here? It's a square. So obviously length into side, LX. LX. Okay. Now rate of change of flux is equal to d phi by dt, which is dBLX by dt, which is BL dx by dt. Okay, for those of you who didn't see the figure, this is a figure. The pink line is the conductor. Okay, conductor can move all the way through X. Okay. Yeah, so this is the rate of change of magnetic flux, BL dx by dt. Now dx by dt is V. We all know that velocity change in displacement by time. So this becomes E is equal to BL V. See, very easy. These are all easy 3 markers. Okay. Students, those who are preparing for exam 3, please be a little more serious because this is your last and final chance. Otherwise, you have to wait for 1 whole year. Please don't do that. You have enough time now. That's why we've started early enough so that you don't have to study on the last minute. Okay? Yeah. Obtain an expression for instantaneous induced EMF produced in an AC generator. Okay. Instantaneous. So this is an AC generator. Okay. So there are slip rings. And then AC generator. So obviously AC current has to be generated. And there is a coil here. Okay. So because if there's a magnetic field and current, together what happens, the coil should rotate. So what happens here is you have mechanical energy. The rotation of the coil is converted to electrical energy using the process of electromagnetic induction. So the coil is rotating. So when the coil rotates, what happens? The magnetic flux becomes VA cos omega t. Theta is omega t. Theta is the angle by which it is rotating. So E is also equal to d phi by dt. So this phi you substitute it as BA cos omega t, and then cos omega t you differentiate, it becomes sin omega t. So epsilon naught is NBAW, then E is equal to what? E naught sin omega t. Omega is 2 pi nu, E is equal to E naught sin 2 pi nu t. So you can see that this is how this alternates. Okay? Next question. Derive the relation between radius of curvature and focal length in case of a concave mirror. So for a concave mirror is a mirror like this where, this just goes in. Okay? It's like entering into a cave. That's how a concave mirror is. So let's learn to draw so in mirrors, lenses and all of that, you find it difficult if you can't understand the diagram. Diagram is the most important thing. So first let me draw the principal axis. Principal axis and then the mirror. Okay, basics first. And then I will put let me try and draw neat figures. Or I can just draw it on top of this. Yeah, I think that will be enough. So this is a principal axis and then this is a mirror. Okay. And then what you should do is the center of curvature. So what is center of curvature? If this is the part of a mirror, if I make a sphere with it, the center of the sphere is the center of curvature. Okay. Now, the focal length is your F, and then the distance between center of curvature to the end is radius of curvature. So this is going to be R. In all the directions it will be R because it is the center of a circle that contains the lens or the mirror. Usually the mirror. Okay, all that is fine. Now let's start with the ray diagram. So this is your object. Okay. So first ray, it is parallel to the principal axis. Any ray parallel to the principal axis should pass through the focus. First ray. Any ray parallel to the principal axis should pass through the focus. Second rule. Any ray that is passing through the center of curvature would pass undeviated. It will take the same path. Okay. Now this is all that is there in the ray diagram. So let's make angles. So initially, the angle of incidence is this. The angle of refraction is this. So they have to be equal. So this is theta, this is theta. Law of reflection. Angle of incidence should be equal to angle of reflection. So theta is theta. Now, if you look carefully, this green and yellow line with respect to this pink line. Okay. So here, this is theta, this is theta. But if you see, aren't these two alternate angles? So if this whole thing is 2 theta, shouldn't this also be 2 theta? That is how this becomes 2 theta. They're alternate angles. Okay. Similarly, these two are also alternate angles. So if this is theta, this is also theta. Okay. These are alternate angles, this and this. So this is theta, we definitely know because that is the angle of incidence. So then this is also theta. Okay, so with the concept of alternate angles, you get theta, 2 theta and all of that. Then if this much is clear to you, then the derivation part is very easy. Yeah. Let's look at the derivation. Let P be the pole, F the focus, C the center of curvature, all of that. So first thing we will take is take triangle MCD. Now can you see? Yeah. MCD. So for MC, oh, yeah, I know what you're all saying. MCD is the other big one, ma'am, no? Yeah, this is MCD. So for MCD, the angle is theta. So tan theta is opposite by hypotenuse. Opposite is what? MD. Hypotenuse is CD. So tan theta is MD by CD. Now you take the violet triangle that I drew first. There tan 2 theta is MD by FD. Opposite by adjacent. Now you take the angles to be very small. So tan theta you approximately take it to theta. Tan 2 theta you approximately take it to 2 theta. So what does it become? MD by CD will be theta, MD by FD will be 2 theta, and then you take the ratio of the two. MD cancels, theta by 2 theta will be 1 by 2, CD will be 2 FD. That's all. Now what is CD and what is FD? CD is the distance from the center to the pole, which is R, radius. FD is the distance from the focus to the pole, which is F. So CD is equal to 2FD is the same as R is equal to 2F. So F is equal to R by 2. It's very easy. All the steps are given here. Okay. Yes. Okay. Conditions for total internal reflection and critical angle. Now, yeah, if this is a surface and let's say this angle of incidence has to be theta c. For that case, the ray must always travel from denser medium to rarer medium. First point. The angle of incidence must be greater than, okay, condition for total internal reflection. Okay. Yeah. The angle of incidence, theta, should be greater than critical angle. Only then this will go in. That's all. Now what happens? For when will it be critical angle? So if this is a surface and this is the equal to critical angle, then what happens? This will be 90 degree. Okay, next question. Prove that law of refraction of a plane wave using Huygens principle. So using Huygens principle, the diagram, there's a diagram. Yeah. So what happens is, you have two mediums, medium 1 and medium 2. Okay. I draw a normal. Here also there's a normal. Now you can see there's an incident wave ray coming. Two incident rays are coming in. I take a point on both the incident rays such that they're at the same position and I connect them. This becomes my incident wavefront. What is wavefront? Wavefront is a group of waves and two waves that are at the same point. When you connect them, you can get the wavefront. Okay. So you can see the wavefront reaches the medium at point A, but at point B, it still hasn't reached. So the wavefront is slanting. Okay, so you can see the wavefront travels down. Now, after some time, it reaches here, but here it reaches here. Now, this purple line is the refracted wavefront. Okay, so the upper purple line AB is the incident wavefront, the lower purple line is the refracted wavefront. Now, let's do the math. So, you just have to find out the angles. So, BC C is this point. BC is V1T from B to C. Okay. This is V1T. What is sine I? Sine I is BC by AC. What is BC? V1T by AC. Similarly, do sine R. This is sine I. This is sine R. Sine I and sine R are not angle of incidence and angle of reflection, but it is angle of incidence of wavefront and angle of reflection of wavefront. Okay? Yeah, this is I, this is R. Yeah. Then what else? Sin R is equal to AE by AC, which is V2T by AC. Now you just have to divide it. Sin I by sin R. V1 by 2. Okay? You get the very famous Snell's law. This is also equal to N2 by N1, which is the refractive index. Okay. Prove the law of reflection of a plane wave using Huygens principle. Same thing. In the previous case, it was refraction. Here it's reflection. So look at what I'm drawing carefully. So this is an incident ray. Okay, this ray is reflected. There's another incident ray that is also reflected. Okay. Now what I do? The two incident rays, I join them to get my incident wavefront. So which are my two incident rays? This one and this one. So I join them, I get my incident wavefront. Now what I do is I take my refracted rays. Okay, sorry. Second refracted ray is not shown, okay. The second refracted ray is not shown. This is the incident. Yeah. So this is your refracted, reflected wave ray. Here you have a reflected wave somewhere here. So you join these two. You get the reflected wavefront. So angle R is angle of reflected wavefront. Angle I is the angle of incident wavefront. Okay. Now you get BC. BC is VT. AE equals BC equals VT. AE equals BC, it's 90 degree. Here you're only proving that angle of incidence is equal to angle of reflection. That is the basics of reflection. So our aim is to prove that reflection, the laws of reflection hold for wave fronts as well. Not just for waves, but for wave fronts as well. What are wave fronts? They are a group of waves coming together. Okay. Next question. Derive the expression for energy of an electron in hydrogen atom in terms of radius. Okay, do I have a figure? Okay, I don't have a figure. So you just have to derive an expression for energy. What is an expression for energy? Energy is equal to, oh, yeah, that we have to find out. So first we'll start, it's a circular radius. So force is mv square by r. Electrostatic force 1 by 4 pi epsilon naught E square by r. You equate the two. So r and r cancels. You will get mv square is equal to 1 by 4 pi epsilon naught E square by r. Okay. Now let's find out kinetic energy. Kinetic energy is what? Half mv square. So I just substitute v square. I mean mv square. mv square you put this and then you will get this. Next is potential energy. U is equal to minus 1 by 4 pi epsilon naught E square by r. So the total energy is kinetic energy plus potential energy, which is E square by 8 pi epsilon naught r minus E square divided by 4 pi epsilon naught r. So you take all the common terms outside. What remains is, so E square by 4 pi epsilon naught r. Afira, which one do you want me to explain again, dear? Is it this question? Afira, can you tell me if you want me to explain this question or Huygens? Yeah. E square into 4 pi epsilon naught r. You take it outside, so what remains? 1 by 2 minus 1, which is... Okay, this question is very easy. So you will get E square. See, you have to derive an expression for energy. Yeah, I'll explain. I'm just going too fast because all the steps I've written here. So, and okay, I'll explain this once again. This is a very easy question. See, you have to derive the expression for energy of an electron in a hydrogen atom. So, this is a hydrogen atom. This is an electron. Okay. The radius is r. So, this is an electron moving in a circular orbit. Anything moving in a circular orbit will have centripetal force. So, centripetal force F is equal to mv square by r. Okay. Now, this electron is held together with electrostatic force also. So, this is 1 by 4 pi epsilon naught E square by r square. We've learned this. Yeah. Now, both of these have to be equal because the electron continues to move in a circular motion. So, mv square by r is equal to 1 by 4 pi epsilon naught E square by r square. So, this r and this r square cancels. So, what does this become? mv square is equal to 1 by 4 pi epsilon naught E square by r. This one is clear? Now what I will do? I will find out the energy. The first energy is what? Kinetic energy. What is kinetic energy? Half mv square. I already have mv square. So kinetic energy is going to be half into mv square, which is 1 by 8. 1 by 8 pi epsilon naught E square by r. That's all, no? 1 by 8 pi epsilon naught E square by r. Okay. Now what is potential energy? Potential energy is the negative of kinetic energy. I mean the negative of general energy minus 1 by 4 pi epsilon naught E square by r. For potential energy, there's actually one derivation which I have not, put here. Okay. That you can refer your books. There is a derivation. Otherwise, you can just remember it as, minus of F. But it's not right. It's just a trick to remember. Now, total energy is what? Kinetic plus potential. You just add the two. Is it clear? Two people had told me. Jennifer, yes, I am a physics teacher. I will do only physics, but our channel has all subjects. Okay. So if you go to Vedantu Karnataka channel, which is the channel that you're watching right now, you have Gopika ma'am and Baswa sir teaching you biology. You have Pramila ma'am and Ankeda ma'am teaching you chemistry. I am Catherine, I'm teaching you physics. We have maths teachers coming soon. Okay, the maths classes will also start soon. Okay. So I think this is clear. Yeah, I verify it's clear. Sorry, Afira. Okay. Hamsu, you want me to explain slow? Okay, Hamsu. I just wanted to, not make the video too long. That's why I've explained it fast. So for all of those portions that we already covered, you can watch the recording. Okay. You can just reduce the speed a little and watch the recording. Okay. I'm really sorry. I'll go slow now. Now, three postulates of Bohr atomic model. So there are three postulates that Bohr said. These are all direct questions. So what did Bohr say? First thing he said is electrons move in stable orbits. So if this is an atom, okay, and our electrons, these electrons, if they're moving in their own orbit, they move with very, a lot of stability. They do not radiate any energy. Okay? Yeah. Now, quantization of angular momentum is what? L is equal to nh by 2 pi. And now the last point is that, so if there is, imagine there are, these are the two energy levels. So I'm just drawing two lines. So there's an electron here, okay? And it gets some energy from some external light source. Some radiation hits on it. It gets energy. It is now Superman. It gets a lot of superpower. So it's like it's telling all the other electrons in its energy level, saying, I am now a superpower electron. I don't want to stay here. I'm going to go up. So what it does, it goes up. It goes to the higher energy level. And then now it is here. But when it reaches there, it realizes they're all not like him. They're all having very high energy, but he has high energy for only some time. After this energy finishes, he will not be able to stay there for a long time. So he realizes he has to go back home. So what he does, he goes back home. When he goes back home, he had some extra energy. He does not need that when he is in his own shell. He does not need the extra energy. The extra energy is emitted. Okay, this is h nu. So what is h nu? H nu is the energy difference. So whatever energy the electron had when it came back, it just emitted it. So h nu is E2 minus E1. Hi Pallavi, I'm good. How are you? Okay. Next, limitations of Bohr's model. So Bohr's model was applicable only for hydrogen-like atoms. Okay. Yeah. It couldn't explain the fine structure of spectral lines and intensities. It does not account for relativistic effects of electron distribution. So these are all some terms that you might not know right now, but you know, these were all limitations of Bohr. So if you take physics in advanced levels and all, you will see all of these are very important. But then Bohr couldn't explain them. Okay? You might think, why would someone need all this? No? Yeah. Next is the explanation of photoelectric effect. Einstein's explanation of photoelectric effect. So Einstein used Planck's quantum theory, okay, and he says that light is made out of photons with energy E is equal to h nu Okay, and so let's say you have a ray of light. This is a ray of light. So this light has what do we say? Photons. This light is made out of so many photons. Okay, and each of these photons they have an energy of h nu. Now, when a photon goes and hits an electron, just like I showed you here, okay, the violet color ray is a photon. It's going and hitting an electron. Okay, so when a photon hits an electron, what happens? Part of the energy overcomes the work function. Remainder becomes kinetic energy of the electron. Remaining, okay? The remaining becomes kinetic energy of the electron. Okay? So what happens? The Einstein's photoelectric equation says that K max is equal to h nu minus phi h nu minus nu naught. Okay, let's see what happens. Photon comes, hits an electron. Okay, let's say this has an energy of K. Okay, so this K, no, this energy is h nu. H nu comes, hits the electron. Sum of h nu. Now, what the electron has is only h nu minus phi naught. Why? Where did some go? Some of it was used to overcome the work function, the energy of the electron. Okay? So now what the electron has is h nu minus mu naught. That will be its kinetic energy. So all of the energy from the photon is not converted into kinetic energy. Some of it is used to overcome the work function phi naught. The rest becomes kinetic energy. Okay? Key observation, emission is instantaneous. Existence of threshold, kinetic energy increases with frequency, current increases with intensity. Okay. Same question, a little more detailed version I put. This could be a 5 marker also. So that's why I put this. Einstein explained photoelectric effect based on Planck's quantum theory. According to Planck's theory, light consists of tiny packets of energy called quanta or photons. Einstein proposed that the photoelectric effect is the result of a single photon colliding elastically with a free electron in the material. So, as I said, same thing. A single photon comes, okay? Photoelectric effect is the result of a single photon coming. It is colliding with a material, okay? A part of the energy is used to overcome work function. Okay, so for those of you who do not know work function, it is a minimum energy required to liberate an electron from the surface. So if there's an electron sitting here, the uh, energy comes, okay? The electron absorbs the energy. The electron absorbs a minimum amount of energy for it to escape from the surface. That is work function. The rest of the energy is what is going to be converted as kinetic energy. Okay? So, if you want to find out the energy of the ray that is coming, you have to calculate, you have to just add the total work function and the kinetic energy. That will just give you the energy of the photon because the energy of the photon is divided into two, the work function energy and the kinetic energy. Okay. Next is binding energy and mass defect. The relation between binding energy and mass defect. Okay. So, what is mass defect? Mass defect is the difference between the total mass of individual nucleons and the actual mass of the nucleus. Okay? So, imagine you have a nucleus, okay? A nucleus with these many protons, these many neutrons, okay? So, if you take the mass of all the protons and all the neutrons, you will get a value. Shouldn't that be equal to the actual mass of the atom? No, actual mass of the nucleus. No electrons in the nucleus. So you don't have to consider electrons. See, you have a nucleus. Let's say you have two protons and two neutrons. Okay? Now, the total mass of the nucleus should be the mass of the two protons plus mass of the two neutrons. But it is not always correct. Sometimes, if you add the mass of protons plus neutrons, you will not get the actual mass. So, there is something called as a mass defect. So, that is why you do this formula. So, you find out the mass of the protons plus the mass of the neutrons minus the whole mass. You will get a small value. That is the mass defect. So, if you look at this formula carefully, mass of one proton into Z, which is the number of protons, plus mass of one neutron into number of neutrons, which is A minus Z. That minus mass of the whole nucleus, you will get the mass defect. The mass defect is the small deduction in the mass. There is some variation in the mass. That is your mass defect. Now, what is binding energy? So, binding energy is the energy required to deassemble a nucleus, to bind it all properly. Okay? Binding energy is given by E is equal to delta mc squared. Now, if it's in joules, you just take it as 3 into 10 raised to 8. If it's in MeV, you take it as 931. Okay? Next, write the three features of nuclear force. Nuclear force is strongest, it's short range, charge independent, shows saturation. What does shows saturation mean? It means each nucleon interacts only with a few nearest neighbors. Okay, so if you have a proton, if I'm a proton and I have 10 people around me, but I only like 5 people, so I'm only going to interact with 5 people. That is because I will get saturated if I talk to 6 people. So I only talk to 5 people. Okay, so that is a feature of a nuclear force, that it can only interact with very few neighbors. Otherwise, it will get saturated. This is the same question. Repeating. Okay. Yeah, saturation we discussed. What else? It is the strongest force in nature. That means it's very strong, even though it's a very short range. Like, you can't see where the nuclear force is. So how can you separate it? It's very small. I mean, the distance is very small, but the strength is very large. That is why that is the second point, short range force, which means they're very close. Okay, it's like my hands are more far apart than two nucleons, because my hand is full of atoms. Inside them there is proton and neutron, and they have the nuclear force. So imagine how short the range is. And they're charge independent. So they can act between a proton and a proton. They can act between a neutron and a neutron. They can act between a proton and a neutron. So they don't care about charges. Okay. So imagine, like I said, if I'm a proton, I can talk to 4 people. If I talk to 5 people, I become saturated. But out of these 4, the 4 can be anybody. It can be boys, it can be girls, it can be aunties, uncles, kids, anything. I don't have a problem. Okay? So it's independent of charge, but I can only talk to a few people. That's how it is. Okay? Okay. Next one. Distinguish between intrinsic and extrinsic semiconductors. So, what are semiconductors? That we will look at. Okay, let's look at. Okay. So, there are 3 kinds of materials: conductors, semiconductors, insulators. Conductors conduct very well. In semiconductors, conduct not very well, but not that bad. Insulators do not conduct. What do you mean by this conduct? It could be conducting heat, conducting electricity. Basically, it allows this to pass through. Okay. A semiconductor allows something to pass through in a controlled manner. So there are two kinds of semiconductors, intrinsic and extrinsic. Okay. Intrinsic is what? It's very pure. An intrinsic semiconductor is a pure semiconductor. Okay. In a pure semiconductor, the number of electrons is equal to the number of holes. And it has a low conductivity, which means it does not conduct a lot. Okay. If you want to use it as a conductor, which means if you want to allow electricity to pass through it, you have to add some impurities to it. In a pure form, it has very low conductivity. It behaves as an insulator at 0 Kelvin, which means that if it's very cold, okay, 0 Kelvin is the coldest temperature. So if it's very cold, it behaves as an insulator. But it is not suitable for electronic devices. Why is it not suitable for electronic devices? Because electronic devices have to conduct electricity. How does an electronic device work? How does my laptop work? There's current passing through all the circuits and all that. But if my laptop is made out of plastic, current cannot pass through because it's an insulator. Similarly, intrinsic semiconductor is a material that does not allow a lot of electricity to pass through. So it is not suitable to make electronic devices. So what can be done to a semiconductor? You can add impurities to it. So when you add impurities to an intrinsic semiconductor, it becomes an extrinsic semiconductor. Okay. So an extrinsic semiconductor is a conductor which has impurities. Now the number of electrons is not equal to number of holes because I have added impurities. So the impurities will have some electrons and holes that will also contribute. So why did I add impurity? To increase the conductivity. Okay. Now this behaves as a semiconductor even at 0 Kelvin. Okay. That is used to make electronic devices. So if I have an electronic device, it is supposed to work anytime. Only then it's a good one. So at a very cold temperature, if it does not work, then it's not useful. And in some physical experiments, you need to operate semiconductors at very low temperature. So that is why you add impurities to semiconductors. Okay? Okay. Okay, match scores are coming up. Alright. Next. Write two differences between P-type and N-type semiconductors. So as I said, now what we are going to do here, extrinsic semiconductors are divided into two. P-type and N-type. Okay. So intrinsic semiconductor is pure. We are not going to use it anywhere. Extrinsic is doped and they are of two types, P-type and N-type. Here. Okay. To write two differences between P-type and N-type semiconductors. So P-type semiconductors are doped with trivalent impurity. What does that mean? An impurity with 1, 2, 3 electrons. Okay. It should have 4 and the fourth place will be a hole. Okay. So its majority charge carrier are holes, minority charge carriers are electrons, has an acceptor level, blah blah blah, all is fine. Now, N-type semiconductor is doped with pentavalent impurity. Pentavalent impurity means it has electrons, 5 electrons. Okay. Majority charge carriers are electrons, minority charge carriers are holes. So if holes are more, majority charge carrier is hole. If electrons are more, majority charge carrier is electron. Okay. So depending on which one is higher, you determine which is majority and which is minority. So what actually happens is you take this impurity, you add it to another semiconductor, pure semiconductor. So let's say the pure semiconductor has 4 electrons. Okay. The impurity has 3 electrons. Now total you have 7 electrons, but you need 8. But you don't have 8. So you have 7 electrons and 1 extra hole. Right? So there what happens? There is a hole. Okay. Now in what otherwise what happens? Imagine you have 9 electrons. You have an extra electron. Then the majority charge carrier is an electron because you have an extra electron and that electron can help in conduction. Okay. What else? Yeah. Next is distinguishing between conductors, semiconductors, and insulators. Except above valence band. Oh, this one. Okay. So these semiconductors have a valence band and a conduction band. Okay. So acceptor level means they can accept electrons. Okay. Because their majority charge carriers are holes, they can accept electrons. Donor level means they have a lot of electrons. So they can donate electrons. Okay. Donor level just below conduction band. So it's just above. There are 2 bands. Okay. Every semiconductor has 2 bands like this. You can see this is the energy band diagram of a semiconductor. There's a valence band and then there is a conduction band. Okay. So valence band, electrons always move from the valence band to the conduction band. So if there are electrons here, they move from the valence band to the conduction band. So if it's a p-type semiconductor, they have an acceptor level just below the valence band, which means here they do not have a lot of electrons to move. So here they have an acceptor level, they can accept electrons and then move. But if it's an n-type, you can see it has a donor level. So here it can donate a lot of electrons. Okay? Because it has a lot of electrons, it can donate. Electrons always move from valence band to conduction band. So if conduction band has to have electrons, it is a semiconductor with a lot of electrons. Okay? Yeah. So, yes, Hamsu, what happened? What is it? Tell me. Okay, now, yeah, conductors, insulators. The main difference between conductor, semiconductor, and insulator is the energy band gap between the valence band and conduction band. So, for conductor, there is no band gap, there is no gap, they're sandwiched, they're very close together. That is why electrons are easily able to flow from valence band to conduction band. Okay, because it does not have to have any energy. It's like you going from one room to another. Even if it's raining, whatever happens, you can easily go. But for semiconductor, there is a little gap. So you need some energy. The electrons in the valence band have to have some energy to jump past this gap and reach the conduction band. But in an insulator, you can see the gap is too large. This gap is too large that an electron can never reach the conduction band. So they never conduct. Okay? So the energy band gap is 0. Semiconductor, it's always less than 3 electron volt. For insulator, it is greater than 3 electron volt. Okay? Example for conductors, copper, aluminium, silicon, germanium, diamond, glass and all that. Now at 0 Kelvin, you can see in the figure. Well, at 0 Kelvin, what happens? Valence band and conduction band overlap. They're together. Semiconductors, valence band is full, conduction band is empty. Okay, which means it does not conduct. For it to conduct from valence band, the electron has to reach the conduction band. So at 0 Kelvin, valence band has a lot of charges, but it is not able to reach the conduction band. Insulator, no conduction, very big band gap. Temperature coefficient, conductor is positive, semiconductor negative, insulator 0. Now conductivity and this one, change in conductivity, it changes with temperature. Conductors, when temperature increases, it decreases. Semiconductors increases. Insulator, no significant change. Okay, so these are all some important 3 markers. You didn't understand this one, right? So, in a p-type and n-type semiconductor, why is there an acceptor level just above valence band in p-type and a donor level just below conduction band in n-type? That's your doubt, right? Isn't it? Is that what you haven't understood, Hamsu? Can you just clear? Can you just clarify? Is that what you didn't understand, Hamsu? See, if I just assume that it is that, see, here, when you talk about donor levels, so as I said, this is a pentavalent impurity, so it has 5 electrons, okay? So the 5th electron can easily be removed. So it can, from the valence band, it can easily go to the conduction band, okay? So it is called the donor level because it is, how do I say? From the valence band, it can easily go to the conduction band because it's an extra electron. It's a free electron. So the energy level where the 5th electron sits is called the donor level. Okay. And it is just below the conduction band. Okay. So the 5th electron is going to be at the donor level. So donor level is a level very close to the conduction band. Okay. Yeah. Yes. Donor level is a level very close to the conduction band. So electrons can easily jump into the conduction band from the donor level. Now in p-type, what happens? In p-type, there are only 3 valence electrons. So 1 is less. So to fill the missing bond, an electron from the valence band can jump to the acceptor atom, leaving behind a hole in the valence band. So acceptor level is very close to valence band. Electrons are taken from the valence band, holes are created. So how do holes cannot move? Electrons have to move. So for electrons to move, you need holes. Yeah, for electrons to move, you need electrons. Yeah, you don't have electrons here. So when these electrons move, there are holes. So they're at the acceptor level. So you can actually, yeah, that's all that you need to know there. Okay, so these are all some 3 markers, some previously asked 3 markers that I have compiled together in one PDF. There could be more 3 markers, but you should know at least these 3 marks. Okay, so if you want to score centum and all that, you have to look into more questions. But if you want to pass, if you want to, score pretty well and all that, you should at least know these 3 markers. But I won't tell you 100% only these will come because I'm not the one who's setting the question paper. But I've tried my best to inculcate 3 markers from almost every chapter. But you need to, if you want a full score, you need to go an extra mile. Okay. So that's it. Yes. So students, if any of you are looking for offline classes, okay, if you're looking for offline classes, please you can visit to Vedantu in Bangalore, offline center in Bangalore, which is in JP Nagar. Okay, so if you want to attend offline classes with the best teachers, with the smartest brains in India, you can go to JP Nagar. Okay. So I hope this was a useful session to all of you. Please let me know in the comments on what other sessions you want and how the session was and if it was helpful to all of you. If there's anything else, you can let me know in the chat now. Otherwise, we can end the session now. You're welcome, Afira. Okay. Yes. Anything else? Was my video lagging or stuck in between? Yes, no. Okay. Yeah. So I'll see you tomorrow, same time with 5 markers. Okay. So students, all those who are preparing for exam 3, please tell your friends Vedantu Karnataka has already started. Okay. Already started with exam 3. So send the link to all your friends. I think the live is already created on our on our channel. You can just go to Vedantu Karnataka, click on live. There will be all the lives, so go there, send the link to all your friends, tell them tomorrow. Yeah, tell them tomorrow it is going to be 5 markers. Okay? Okay, thank you, Afira. Afira says it was helpful. Okay, so see you